Okay, so we're getting into arithmetic sequences and series. We're going to be doing a sequences and series unit, starting today with arithmetic. So everybody, a sequence of numbers, for example, 1, 2, 3, it's just a sequence of numbers here. Now this one would be considered arithmetic because it has what's called a common difference. Difference means subtraction. So everyone, can't you see that we're adding 1 each time? Yes? But we really actually do, we work backwards with this. We say, okay, 4 minus 3 is 1. 3 minus 2 is 1. 2 minus 1 is 1. So we were adding 1 each time. So we had a common difference of 1, so it's arithmetic. Now we can have many types of sequences. I could have a sequence of a bunch of random numbers, and the pattern could be completely different. Like I could be adding 1, then 2, then 3, then 4. And yeah, there's a pattern to it, you know. I'm adding 1 the first time, then I add 2 the second time. That's not arithmetic. Arithmetic has to be the same. So what we're learning, all the formulas we're using today only works if it's arithmetic. Okay, let's look at this one. Is this one arithmetic? Yeah, if you subtract that, you get 5. That minus that is 5. That minus that is 5. So yes, it's arithmetic because we have a common difference of 5. Everybody good? Okay, tell me if 1 through 10 are arithmetic or not, and if they are, state the common difference. Quickly. Okay, what was hard about this unit for me, I've realized when I became a teacher, was that I did not understand the notation, how things are written, what it was saying. So let's go over that first of all. So everybody, this is how you're going to see things in written with sequences, the notation you'll see. So a sub 1 literally means the first term in the sequence. So our first term in the sequence is 2. This would be our second term, third term, fourth term. Does everybody see? Those little sub signs are just telling you, those little mini numbers are just telling you what term you're at. So a sub n is the nth term in a sequence. Any term in a sequence. So if I said to you, find a sub 12, what term would I be asking you to find? The 12th term, right? Now notice, 1 didn't have anything to do with this 2, did it? That just says the first term. I used to think it was related somehow. It's not. Okay, now next thing, this a sub n minus 1, this a sub n minus 1, this little minus 1 should be written a little smaller. That minus 1 is down here with an n. That literally just is saying the previous term, or the term before a sub n. Because think about it, look. If I set some a sub n, if I'm talking some a sub n, won't a sub n minus 1 just come before a sub n? Yeah. So that is just saying, there's no math behind it, n minus 1. So what about the minus 1? No, that's not what it's saying. That literally just says the previous term. So then a sub n plus 1 would be the term after, or the next term, for example. So let's test your notation abilities. If I said to you, given a sub n is equal to, looking up here at number 1, is 3, what's a sub n minus 1? What would you say? 2, right? That's literally just saying what's the previous term. Do you guys see? I've got 2. Okay, awesome. If I would have said, given a sub n is 5, what's a sub n plus 1? 8. Okay, good. We understand the notation. Great. Okay, so now let's go ahead and write a formula for any term in the sequence. Meaning, how do I generate those numbers? 1, 2, 3, 4. What is a formula that generates that? Now we're going to write our own formula. One that's easy to write. You're not looking at anything. This is one that's easy to write. What do we see happening? Aren't we starting with 1? And then what are we doing? You're saying we started with 1 and then we added 1. So let's write a formula. So we'd say a sub n, any term in the sequence, right, will be, so aren't we really just taking the previous term and adding 1? Previous term, add 1. So let's try that. A sub n minus 1, take the previous term and then you add 1. Wasn't that easy to write? It's just what you see happening. Now here's the thing. If I said to you, take the previous term and add 1, you'd say, okay, I can do that, but where do I start? So we didn't specify starting the a sub 1 equals 1. Otherwise, you wouldn't be able to recreate 1, 2, 3, 4, because you wouldn't know where to start. You get what I'm saying? Yes? Okay, let's write our formula for this one. Any term in the sequence will be take the previous term and what? 5. Add 5, right? And then that is, if for this one, if we start at a sub 1 of 3. And then I could recreate it. 3, 8, 13, 8, because I know what to do based on the formula. Now that formula is really nice and easy to write. We like this formula to write because it's called a recursive formula. A recursive formula formula, so that's what this next piece is saying. A recursive definition or a recursive formula, which you have a formula sheet. I would be writing this on there. This is actually not written on the formula sheet, this part. A recursive formula is one that is easy to write because you literally just write what you see happening. Now here's the problem. Is it really even usable? Is the formula usable? Not really. Like for example, if I said to you, look at number 11. We have a 12, 14, 16, 18. Let's write a recursive definition. A sub n is equal to, you take the previous term, and aren't we adding 2? And you'd say, as long as I start with a sub 1 of 12. Great. Now, if I ask you to find the 49th term, is that formula going to be helpful? It would take, I'd have to know the 48th term. I'd have to go clear out. So the formula is not useful. We can write it, but it's not useful. So what formula would be useful? That's an explicit definition. This is a different type of formula we can write. I put a heart by it because we like this one better. This one is a little bit harder to write, maybe. You have the formula on your formula sheet. This one is there. This allows us to find any term in the sequence, and you just plug and chug. You do not need to know anything. You don't need to know any of the previous terms. So that's nice, because that's what we want. So it is a sub n is equal to a sub 1 plus n minus 1 times d. That is a formula you need to have memorized, along with how the recursive definition works. I'll make sense of why this formula works in just a second. It makes complete sense, and you will see it once we use it. So let's write a formula that will allow us to find any term in the sequence here, using this explicit formula. So you'd say a sub n, any term in our sequence is equal to, using this formula, a sub 1 is 12 plus n is, we're leaving n general, because I'm writing a general formula, so n minus 1, and then our common difference is 2, so then times by 2, just plugging it into the formula that I gave you on that formula sheet. Now, that is our answer, but it can be simplified. Let's practice simplifying it, so distributing 2n. So then we have 12 plus 2n minus 2, so a sub n, any term in our sequence, will be generated by the formula 2n plus 10. This formula you can now use to find any term in the sequence. So now I can say to you, find the 100th term. And you'd plug in 100, wouldn't you? A sub 100, plug in 100. If I say find the 43rd term, you take 43 and plug it in right there. Ready, go, plug it in. Well, it's as on the homework it says find the 43rd term. So plug it in. 2 times 43 plus 10 is 96. So a sub 43, our 43rd term, was 96. Wasn't that a lot easier than writing them all out? Yeah. The general formula allows you to find any term in the sequence. And notice, this is going to make a good connection for later. This formula right here is what is creating 12, 14, 16, 18. Do you agree? Plug in a 1, because that's the first term, and you get a 12. Plug in a 2, you get 14. You guys see what I'm saying? Okay. Let's do another one. Number 12. So it says, find the 43rd term. I highly recommend to practice writing a general formula. There's a reason. So you'd say, any term in our sequence, we're going to use an explicit definition, because that's how we can find it, actually. So you'd say a sub 1, which is 13.1, right? Plus n minus 1 times by the common difference. Let's try and find that. This minus this, this minus this, this minus this. Negative 10, negative 10, negative 10. Our common difference is negative 10, so then times by negative 10. Just plugging it into our formula that I gave you on that worksheet. Now let's simplify it, So we have a sub n is equal to 13.1 minus 10n plus 10. So any term in our sequence will be able to be found by negative 10n plus 23.1. Now I can find the 43rd term. I would plug it in. When you plug it in, you would get negative 406.9. Yes?
Didn't we already learn how to plug in our numbers on the stat on our calculator and then just use linear regression calculator? So don't really have to do all that work. And we can just have the calculator give us the number.
So you're saying that you're recognizing that this is, what would your y values be? How would you type that in?
That is the y value.
What would your x? Oh, you just write 1, comma 2. I never thought about that.
Yeah.
It is all arithmetic will come out linear. Yes. But you're not even. Here's the thing. There's going to be a whole portion of the test Like we can't use our calculators on this one. We have to have it under our desk. Because for calculus, you can't even use a calculator in calculus. And this is something you have to know. Okay. So, ready? Oh, wait. I want to show you how the formula literally makes so much sense. It should be easy to memorize because watch it. It actually makes sense. That's what's so cool about it. Look back to number 11. Okay? Now, looking at how this formula is making sense here, let's plug it in. We were asked to find a sub 43, right? So this was the general formula. Let's see why that general formula makes sense. Okay? So we're starting with 12, aren't we? And then we have to add 2. Add 2, add 2. Well, I'm going to keep going, and how many more 2's am I going to need to add? Well, 43, guys. How many times, starting with 12, how many 2's am I going to have to add? 42 of them, right? Because we started with 12, isn't there 43 total terms? You guys see? So look, that formula is literally saying that. Start with 12, so start with 12, we are adding 2, and then 42 times. Because if you plug in 43, do you see how you get 42? Starting with 12, we are adding 2, 42 times. Do you see how the formula does make sense? Yeah. See, look. We started with 13.1. We added negative 10, 42 times. And that would put us out there at the right place. So it makes sense. Okay, awesome. Go do a couple on your own before we move on, but quick. Okay, so we get now that an explicit formula generates that sequence of numbers. And it also allows us to find any term in the sequence. So now go to 21. It says find the missing term of each arithmetic sequence. There are 2 ways to do it, and both ways are important to know because one of the ways will only work sometimes. Like, let me explain. We could go through and solve directly for this value, couldn't we? So we have to set up a true statement. Isn't it true that if it's arithmetic, this minus this will be equal to this minus this, will be equal to this minus this, and so on? Yes. So say that. 49 minus x needs to be equivalent to x minus 23 since we work backwards. Common difference. And now we're just solving for x. Add x, add x. Add 23, add 23. So now on this side I get 72 equals 2x. Therefore x equals 36. We just solved directly for it. 23, 36, 49. Yeah. So we just set up a true statement and then used algebra to solve, right, everyone?
Yeah, come on. You're expecting so much of it.
I know, right? Okay, now here's the thing though. Here's when it becomes a problem. What if you have something like 2 blank blank 16? Now you can't call both of those x's. They're not the same x. Do you guys see how that? Now we're kind of like a little maybe stuck. You guys see? So here is, yeah, you have to use x and y, but then you have 2 unknowns. So how do you solve that, you know? So let's look at it a different way. Instead of solving for x, let's solve for what, stop talking about x. Instead of solving for x, let's solve for what we're adding by each time. So this is how my algebraic framework set up a true statement. Isn't it true that starting with 23, don't we need to add something, add that same something, and we get 49? So 23 plus something equals 49. 23 plus 2 somethings equals 49. So then subtract 23. 2 something equals 26. Question mark equals 13. Now we didn't solve for x, we solved for what we added. So we added 13 each time, added 13. So now you would do 23 plus 13 and you get 36. So instead we solved for what we added for and then we just did it. Now that's what we would do in this scenario. So let's do one more like that and then I'm going to let you go for it on your homework. Okay. That's just how my algebraic brain sets it up. So like right here it says, on the test I'm not going to give you one that is that easy. It says, what are the second and third terms? So you'd say 100 plus, now people cannot, don't do it in your head. The number of somethings is where people mess it up. Starting with 100, I draw my little arrows. Plus something, plus something, plus something. How many plus somethings? 3 somethings equals 82. Now from there, divide by 3. Does everybody see? Then I know what I was adding each time. So question mark comes out to be -6. So we were subtracting 6 each time. So then you do 100 minus 6. So then you'd get your 94. And subtract 6. So you'd get your next term. Are we good with that? Okay. Either way works though. So go do 21 through 32. Okay, go to 33. So this is when this math actually starts being like used. So, a teacher, let's read it. A huge portion of the test is story problems because that is asking the exact same thing that I was asking, it's just in words. So, on the other problems. Let's read it. A teacher donates the same amount of money each year to help protect the rainforest. At the end of the second year, she has donated enough money to protect 8 acres. I kind of drew myself out a little picture. That was the second year, right? She protected 8 acres. Then the third year, she protects 3. Wait, what? What does it say? 12. Oh yeah, 12 acres. Sorry, I'm reading it from up here. Like up close is hard. And then it says dot dot dot. How many acres will the teachers protect at the end of the 10th year? So aren't we wanting this year? Right? Now we'd say, okay, so we're asked to find the 10th term, aren't we? So you'd say a sub 10 is equal to a sub 1. Uh-oh, that's a sub 2. What's a sub 1? Yeah? Yeah, so we have to use 4. Okay? Then plus, and then n is 10, minus 1 times by our common difference of 4. So you calculate it, and at the end of the 10th year, on the 10th year, she's going to be donating 40 acres. Does that make sense? Find this? Okay. Okay, now we're going to go on to the next thing, which is the next page over. Sequences and series. We just did sequences. Sequences of numbers are separated by commas. Here is a sequence. Here is a sequence. Commas are sequences. Now we're going to get into actually adding those numbers. So notice it has the same pattern here. It's just instead of commas, there's addition signs. Addition signs are called series. So now that gives it meaning. This is saying we have some pattern, great. This is saying add up those things. Actually sum them up. So this is considered a finite sequence. We have to know finite versus infinite. Finite means it's finite. You know where to start and stop. Does everybody see? So this is a finite series. We know to start at 6 and stop at 18. So we know we're starting at 6 and adding till we get to 18. Infinite means we don't know the end. It goes to infinity, either on the beginning or the end. This pattern will continue forever, right? Now think about it. If we have an infinite series, it's going forever this way. If I start adding, am I ever going to know when to stop adding? Nope. I'm literally going to be adding forever because that goes on forever. It approaches infinity, right? So I cannot find the sum of an infinite arithmetic series because I would never know when to stop adding. If it's finite, we can find the sum because we know where to start and where to stop. Does that make sense? Okay, awesome. Now you have this formula written down. Here is a formula to actually find the sum of an arithmetic series. The formula is going to be really useful because you're not always going to have things as easy as number 1. Number 1 is making a point here. Yes, it would be easier to just add them up. We're not going to have stuff like this. This is getting you to be able to see how the formula works. So everybody look at your formula. The S of n is equal to n over 2 times a sub 1 plus a sub n. You have to understand what these things mean for it to be easy. N is the number of terms you're summing up. I write myself a note. The number of terms you are summing. A sub 1 is obviously the first term, right? And a sub n is the final term in the sequence. So a sub n is the last term you're summing up. The final term, the stopping point, essentially. So let's look at this right here. Yes, if you were to just add it up by hand, you get 25. Okay, everybody look. A sub 1, 2, 3, 4, 5. Here's a sub 5. Are we good with that? So how many terms are we summing up? The first through the fifth. So that'd be 5. So you'd say I'm summing up 5 terms, which is equal to, plugging it into the formula, n over 2. So that's 5 over 2 times a sub 1. What's a sub 1? 1. And then plus a sub 5, right? Because that's a sub 5, a sub n. So that just means the last term. So plus 9. Start n. And you type it in, you get 25. So the formula is going to be useful when we get things that are not so straightforward, like number 1. Let's do number 2. So, paying close attention here. So you'd say, okay, it says find the sum. So you'd say here's a sub 1, a sub 2, obviously, dot, 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 a sub, we don't know, actually. Do we? Now think about it. To plug it into the formula, we need to know how many terms we're plugging in. How many terms we're summing up. So if this is a sub 20, then we're summing up the first through 20th term. If we're summing up 10, then this would be a sub 10, right, everyone? So what we're going to do is we're going to push pause on finding the sum, because we've got to first find what n is. So go back to your explicit formula. Your explicit formula is what is creating 5, 8, 11, dot, 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 26. So let's write down. Explicit formula for arithmetic was a sub 1 plus n minus 1 times d. That is what is creating these values, correct? Okay, now let's plug in what we know. Our a sub n is 26. A sub 1 is 5. Plus, we don't know what n is. That's what we're trying to find. And our common difference is 3. So now look, do you see how we have everything except for n? And now we can solve for n. Subtracting 5, 21 is equal to n minus 1 times 3. Divide by 3. 7 is equal to n minus 1. Add 1. So n equals 8. This is a sub 8. Okay, so we're summing up the first through 8th terms. So we're summing up 8 terms. Now we can plug it into our formula. So 8 over 2 times by a sub 1, which is 5, plus a sub n, which means the last term, which is 26. Calculate it. $124. You good with that? Do you want another example? Number 3? No, let's do 3. Okay, so you'd say, okay, a sub 1, this is a sub n. We need to know what n is, or else we can't know how many terms we're summing up. So go back to your formula. A sub n is equal to a sub 1 plus n minus 1 times d. Plug in what you know. A sub n is 44 in this one. Our a sub 1 is 4 plus n minus 1, and our common difference is 5. Subtract 4. So we have 40 is equal to n minus 1 times 5. Divide by 5. 8 is equal to n minus 1. So n equals 9. It's just algebra. So now we know we're summing up 9 terms. The sum of our 9 terms will be equal to 9 over 2. Plug it into our formula for sum. A sub 1 is 4 plus a sub n is 44. Calculating it, and you get 216. Okay, go do number 4, go. Okay. Is standard form or factor form better? Neither. Yeah, it depends. Neither. They're equivalent, aren't they? It's just one's in apple and one's in squished apple or whatever, okay? Now, what we're going to do is we're not going to learn how to write something. Oops, I didn't mean to put commas here. We're going to learn how to rewrite this series in just a different format. This is what we just did, right? We just summed up stuff. We're not going to actually, we could find the sum. That's not what I'm asking us to do right now. What I'm asking us to do is take and rewrite this in a different form. So it's called summation notation. So this is what it's going to end up looking like in summation notation, but understand they are equivalent. They mean the exact same thing. Now let's see how this could work, okay? So first of all, the Greek capital letter sigma, this sign right here, is a summation sign. That literally means find the sum. Isn't that what these addition signs mean? Find the sum. So these mean the same thing. Find the sum. Now, let's see how many terms we have. Here's a sub 1, 2, 3, 4, 5. Here's a sub 5, right? So the first through fifth term. This is saying the same thing. find the sum of the first through fifth term. Do you guys see? And then you're like, well, of what? Well, the formula that creates 3, 6, 9, 12, 15. So it'd be the explicit formula, which creates the 3, the 6, the 9, and the 12 and the 15. You guys see what I'm saying? They mean the same thing. So where did I get the 3n? I went and plugged in. A sub 1 is 3 plus n minus 1 times by d. Our common difference is 3. So then that's 3 plus 3n minus 3. So then that's where I got 3n. That's creating the 3, the 6, the 9, the 12, the 15. Good? Okay. So right here would be an infinite series. Find the sum of the first through the infinite. Can we find the sum of an infinite arithmetic? No. So that one wouldn't have a sum. Okay, good. Okay, let's do one off the homework. Rewriting this in summation notation. No different, it's just writing it in a different notation. So you'd say, okay, it's asking us to find the sum. So find the sum. That's what the addition signs mean. Find the sum of the 1, 2, 3, 4. This is a sub 1, this is a sub 4, isn't it? So we're summing up the first through the fourth. That's what this is called a lower limit. So the first through the fourth term is what we're summing up. And then where did we get 4, 8, 12, 16 from? The formula that creates that, which is our explicit formula. We go, I'm going to go do it down here. We want the simplified formula here. So a sub 1 plus n minus 1 times d, plug it in. A sub 1 is 4 plus n minus 1, our common difference is 4. So simplifying that out, you get what? Yeah, so you get 4n, right? They mean the same thing. Okay, another one. Number 9. Now you're going to see that we're going to run into a stopping point for a second. So you'd say, okay, rewriting it in summation notation. So you say, okay, now I'm finding the sum of the first, a sub 1, 2, 3. Uh-oh, we don't know. How many terms am I summing up? I don't know, do I? Just like back to the sum, didn't we have to first find what n is? Yes. We're going to have to say push pause on rewriting it. I need to know if that's a sub 10, 20, 30, you know? Yep. So you go a sub n is equal to a sub 1 plus n minus 1 times d, plug in what you know. A sub n is negative 5 is equal to a sub 1 is 10 plus n minus 1, our common difference is negative 3, people. Work backwards. 4 minus 7 is negative 3. 7 minus 10 is negative 3. Are we good? Yes. Okay, so now solve for n here. So subtract 10. That's negative 15 is equal to n minus 1 times by negative 3. So divide by negative 3. 5 is equal to n minus 1, so n equals 6. So this is actually a sub 6. So now you could say the first of the sixth term is what we're summing up. And what created the 10, the 7, the 4, and the negative 5 was this piece, wasn't it? Yeah. So that would be negative 3n. And then right here, a negative and a negative is positive. So we'll have a 10 plus 3. So plus 13. They mean the same thing though. So how could I undo this? Plug in a 1, I get a 10. Plug in a 2, I get a 7. Plug in a 3, and so on. Plug in a 6, I get negative 5. You see how they're just equivalent? Yes?
Always going to be n equals 1?
For us, when we create it, yes, because we're always going to call this our first term. Does that make sense? We're always going to call this our first term. So it'll always be 1 for us. Okay, awesome. So go do 1 or 2 by yourself real quick before we actually go the other way now. After that. Instructions. Okay, so this says find the sum of each finite series. This is no different than having it written out. This first time I am going to write it out so you can see what's happening. So this is the same thing as saying we're taking the sum. That means we're going to be adding the first through the fourth term. So a sub 1, 2, 3, 4, right? We're summing the first, second, third, and fourth term up, right? So what is our first term? 1 minus 1 is 0 plus. Our second term would be 2 minus 1 is 1. You guys understand that this formula gives us these values, right? Okay. Plug in a 3, we get a 2. Plug in a 4, we get a 3. So we are summing up the first and fourth terms, and yeah, you could just do it by hand. Let's use our formula though, because really it's not going to all be this easy. So you'd say the sum of 4 terms, look, 1 to 4, that's 4 terms, right? I'm summing up 4 terms, so you'd say the sum of 4 terms is equal to 4 over 2 times a sub 1, isn't that my a sub 1? Plus a sub n, isn't this my a sub n? 3, so was it necessary to have all this middle stuff? No, not to find the sum. So next time I'm not going to write it all out like that. All I need to calculate is the first term, which came from plugging in the lower limit, didn't it? My final term, which was plugging in the upper limit, and then we need to know the number of terms we're summing up. So let's do another. Oh, what was the sum? 6. Okay, awesome. Let's do another one. Now this one, when we write our own, we always start with the first term. But this one's saying start with the second term and add up to the 6th term. It's like skipping the first term, which is fine. So we're adding up the 2nd through 6th term. How many terms is that? Yeah, it's 5. Now watch. 2, 3, 4, the second term, 2nd, 3rd, 4th, 5th, 6th. 5. Now we don't have to do it on our fingers, so let's do some math and think about it. 6 minus 2 is a difference of how many units? 4, but that doesn't account for this starting unit. So that'd be 5 terms total. So you do the top minus the bottom, but then you gotta account for the bottom, so add 1 each time. So that'd be 5 terms. So you'd say the sum of 5 terms is equal to 5 over 2 times a sub 1. How do I find my first term? Plug in the lower limit. So plug in a 2. That'd be 4 minus 1. 3 plus the last term you're summing up would come from your upper limit. 12. Plugging in a 6, you get 12 minus 1, which is 11. So then you'll just calculate it. The sum of our 5 terms is 35. Sweet. 35. Okay, can you do those on your own? Okay, awesome. Now, I'm almost done, actually, with the lesson. Then we'll have the rest of the time in class to just work. Let's look at the difference. The hard part is when people get to the test, they don't know if they should be finding the sum or they should just be finding the nth term. So let's read the same problem. This was 33. We've already done it. The teacher that's donating the acres, right? It asks us how many acres will the teacher's donations protect at the end of the 10th year. So that was just finding a sub 10, wasn't it? Now let's read, because on the test you got to be able to separate the two. Which one's which? It wasn't asking us to sum up, right? It said how many acres did the teacher donate at the end of the 10th year? So that would have been a sub 10 only. Now what if they would have said it like this? How many acres will the teacher donate over the 10 years? Do you see how that one would now become, I got to sum up all those things. So now you'd be like, okay, instead of, I've got to do the sum. So it would have been 8 plus 12. But then our first year was 4, right? And then you would have to go through and say, up to a sub 10. So wouldn't I need to find a sub 10? Because then I need it for the formula. You need the last term. Okay, awesome. Yes, you have a question, Steph?
Yeah, just because, like, isn't the formula by itself, whatever the n, 4n, isn't that accumulative on its own?
Nope, that's just finding the 10th term. At the 10th term, you'll have done 10. You'll have 10.
So, like, the 40 acres she donates, whatever, like, that's accumulative from, like, year 1.
Yeah, so, but how many total? You'd have to add up the first year she did 4, plus the next year 8, plus the next year 12, plus the next year, that would be total.
But if she's donating the same amount of money each year, then why is it getting more and more acres?
Like, put it into, like, pretend you have a dollar bill on your desk, and you get $2 each day. And I say to you, how many dollars are you going to have on the 10th day? You'd say? $10, guys. If you start with $1. Oh, and let's say you add $1 each day. Let's make it easy. How many dollars are you going to have on the 10th day? $10. Right? How many? No, you don't. You gained an additional $1 each day. So we didn't actually, it's not $10. Was it $10? But how much total dollars? How much total dollars do you have?
I don't know.
Dude, you have $1 on the first day. The second day, how many dollars do you have?
$2.
On the next day, how many dollars do you have?
$3.
Next day. No, you.
What?
Yes?
Yeah.
What the freak? Are you guys confused about? The next day 5, the next day 6, the next day 7, the next day 8, the next day you get $9, right? Additional dollars. You guys get that word? It's additional. This is what makes it arithmetic. The next day 10. How many total dollars do you have? 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10. You don't have $10. You have all of that.